best option for recycling purposes actually is to leave it as is. Just cover it, make sure that there's no dust formation. Well, actually, I found that out in retrospect already. But the thing is, you know, when you're dealing with bomb squad, and they actually made a big thing, what happened was the actual option we used is we mixed it with water. Why did you mix it with water? Well, because we have to stabilize it, and because the bomb squad didn't want to leave it as is. I don't know about you, but when men have guns, I don't disagree with them. All right? So even if I already actually suggested, and that's not making fun of them, okay? But even if I already mentioned to them that, you know, one of the options is actually leaving it as is, they said, you know, the crowds are gathering and everything else, and then they said that you want them to believe now, after we have said that there's explosion hazard and this and that we will leave the same thing there? No, it cannot happen. So you see, there are certain things that you have to compromise and this and that. So we actually mixed it with water. The powder did not react with water because, this I found out later, because the micron size might not be small enough. There's a certain micron size that makes it reactive with water, or it may already have been oxidized. Because it's an open top and it's not an airtight kind of situation, so it may already have been oxidized. So that means the reaction has been completed. Okay? So that's my favorite incident right there. Next incident. Question? Okay, the question is, how did we accomplish mixing it with water? As a knowledgeable person, we have to, of course, get small portions of the aluminum powder first, put it in a watch glass, and then try it with first cooking oil, and next try it with water. Now, why did I even suggest water? Because I know it's not sodium. I know I have experience with sodium. Just a small drop of water in sodium, and it's just loud bang. And I have experienced it, as I said, but it was not my fault, remember? Anyhow, so with aluminum powder, we just did it in the watch glass, tried it very small portions first. The cooking oil did not mix readily. So that means we have to stir, we have this and that, and it's going to be tedious and so on and so. But with water, it just becomes wet real quickly. So we got to do the water, and then we just use water hose after the test on the watch glass, and we did not see any kind of difference in temperature, no reaction whatsoever, because it's already been oxidized anyway. So, and then we poured water so that, and then it stayed there. Anhydrous ammonia release. Blocks of ice. Remember I talked to you about colligative properties, boiling point, freezing point? They use brine water. Release happened at ice plant. It was left overnight. Brine water saturated with ammonia. The brine water is a salt solution, so that the freezing point of that brine solution is way lower than 0 degrees centigrade. So that if they cool the brine solution, then anything in it will freeze first. I mean, any water, any liquid blocks of water will freeze before the brine freezes because of the colligative property of brine water. But then, because of the release was left overnight, the brine water became saturated. This is like a big warehouse. It's like a 50,000 square foot warehouse plant. Okay, so it's really big. But then the problem is there's a middle school yards away from the plant. What do you do with the ammonia? I know I spoke with Air Quality Management District before. Ammonia is not ozone, depleting or anything like that. So they're not really very strict. They're not very strict. It's not a CFC or anything like that. So actually, one option would be to just release it gradually, you know, so that nobody will be affected. But then the problem is there's a middle school yards away from the plant. And the melting ice also was contaminated. Melting ice and brine water acted as the source of ammonia vapor. Even when we removed the ammonia vapor from the refrigeration equipment, and even if the release was already stopped, meaning all the valves were closed, there's no more source of ammonia, there is still, the source of ammonia is still the melting ice and the brine water. What's the resolution? The plant was closed as airtight as possible. Only one roll-off door was opened. Okay? Picture that. A warehouse, there's only one roll-off door open. An industrial blower was used to vent it. Somebody in level A went in, put inside an industrial blower. Vapors captured using water curtain. When we turned on the blower to blow out the ammonia vapor, we have to use a water curtain on the roll-off door to capture the vapor. We cannot just let it go to the atmosphere, although we could have done that too gradually so that there's no public health impact. But then, because there's a middle school, we had to use a water curtain. Water curtain, but actually we just use sprinkler kind of valves kind of thing. So we had to close it airtight first, and then we had to fabricate the water curtain. Anyway, there was no traffic, there's no freeway involved, so we're not under time pressure for this one. So runoff collected for possible sewer disposal. But then afterwards I found out that the sewer company, LA Sanitation Districts, did not allow for sewer disposal because there were some other heavy metals from the runoff. Ice removed as contaminated industrial waste. Okay? Last is spontaneous combustion. You see, we're still early. Yay! Spontaneous combustion. There was a fire at a single-family dwelling, SFD, in a roll-off bin of trash. Ambient temperature reached over 100 degrees Fahrenheit. Summer, Los Angeles. Single-family dwelling being remodeled with paints and stains. You know those wood stains, you know, for the doors and things like that? So those are organic, right? Organic. Remember what we talked about? Slow combustion, slow versus rapid combustion. Now this one is the slow one. Waste paints and rags scattered about. Resolution. The trash was sorted. There was a fire, of course, right? There was a fire. So the fire department, the fire station, local fire station extinguished the fire. Okay? So for the investigation, what we did was we sorted the trash. There was no source of ignition found. Cigarette butts or matches or flares or anything. There was no possible sources of ignition found. But we saw rags contaminated with wood stains found in the bin, partly burnt. And the thing is, the rags were like, rags with wood stains were like thrown out, disposed of, like bundled up, you know, like it's not spread out thinly, you know, and that's what happened. Contractor and homeowner cautioned about spontaneous combustion. You see, the thing is, when rags with wood stains are like rolled into like crumpled kind of situation, there's slow oxidation in the molecular level, and when there's a slow oxidation of the wood stains, and of course the rag is combustible, right? So slow oxidation at the molecular level makes it hot slowly, and then also because of the temperature, it just ignites by itself. That is spontaneous combustion. Now, you see, there are things that even chemistry cannot explain, because I can explain it because of spontaneous combustion, but the thing is, had they not crumpled the rags and they spread it thinly, then the temperature would not have been reached to fully burn the rag, and that started the fire. You see, slow oxidation of organic stains on the molecular level gave off heat enough to ignite combustible materials nearby. Spontaneous human combustion? That's another story, okay? That's for the Star Trek crowd, okay? So any other questions? That's it. Thank you very much.